Die casting is a metal casting process that is characterized by forcing molten metal under high pressure into a mold cavity. The mold cavity is created using two hardened tool steel dies which have been machined into shape and work similarly to an injection mold during the process. Most die castings are made from non-ferrous metals, specifically zinc, copper, aluminium, magnesium, lead, pewter and tin-based alloys. Depending on the type of metal being cast, a hot or cold chamber machine is used. The casting equipment and the metal dies represent large capital costs, and this tends to limit the process to high-volume production. Manufacture of parts using die casting is relatively simple, involving only 4 main steps, which keeps the incremental cost per item low. It is especially suited for a large quantity of small to medium-sized castings, which is why die casting produces more castings than any other casting process. Die castings are characterized by a very good surface finish and dimensional consistency. 2 variants are pore-free die casting, which is used to eliminate gas porosity defects, and direct injection die casting, which is used with zinc castings to reduce scrap and increase yield. History: die casting equipment was invented in 1838 for the purpose of producing movable type for the printing industry. The first die casting-related patent was granted in 1849 for a small hand-operated machine for the purpose of mechanized printing type production. In 1885, Otto Mergenthaler invented the linotype machine, an automated type casting device which became the prominent type of equipment in the publishing industry. The SOS die casting machine, manufactured in Brooklyn, New York, was the first machine to be sold in the open markets in North America. Other applications grew rapidly, with die casting facilitating the growth of consumer goods and appliances by making affordable the production of intricate parts in high volumes. In 1966, General Motors released the Acrylic process. Cast metals: the main die casting alloys are zinc, aluminium, magnesium, copper, lead, and tin. Although uncommon, ferrous die casting is also possible. Specific die casting alloys include ZAMAK, zinc aluminium, aluminium 2, for example. The Aluminum Association standards, AA380, AA384, AA386, AA390, and AZ91D magnesium. The following is a summary of the advantages of each alloy. Zinc, the easiest metal to cast. High ductility. High impact strength. Easily plated. Economical for small parts. Promotes long die life. Aluminium, lightweight. High dimensional stability for complex shapes and thin walls. Good corrosion resistance. Good mechanical properties. High thermal and electrical conductivity. Retains strength at high temperatures. Magnesium, the easiest metal to machine. Excellent strength-to-weight ratio. Lightest alloy commonly die cast. Copper, high hardness. High corrosion resistance. Highest mechanical properties of alloys die cast. Excellent wear resistance. Excellent dimensional stability. Strength approaching that of steel parts. Lead and tin, high density. Extremely close dimensional accuracy. Used for special forms of corrosion resistance. Such alloys are not used in food service applications for public health reasons. Type metal, an alloy of lead, tin and antimony, is used for casting handset type in letterpress printing and hot foil blocking. Traditionally cast in hand jerk molds, now predominantly die cast after the industrialization of the type foundries. Around 1900 the slug casting machines came onto the market and added further automation, with sometimes dozens of casting machines at one newspaper office. Maximum weight limits for aluminium, brass, magnesium, and zinc castings are approximately 70 pounds, 10 lb, 44 lb, and 75 lb, respectively. The material used defines the minimum section thickness and minimum draft required for a casting as outlined in the table below. The thickest section should be less than 13 mm, but can be greater. Equipment: there are 2 basic types of die casting machines, hot chamber machines and cold chamber machines. These are rated by how much clamping force they can apply. Typical ratings are between 400 and 4,000 a street. Hot chamber die casting. Hot chamber die casting, also known as gooseneck machines, rely upon a pool of molten metal to feed the die. At the beginning of the cycle, the piston of the machine is retracted, which allows the molten metal to fill the gooseneck. The pneumatic or hydraulic-powered piston then forces this metal out of the gooseneck into the die. The advantages of this system include fast cycle times and the convenience of melting the metal in the casting machine. The disadvantages of this system are that it is limited to use with low melting point metals and that aluminium cannot be used because it picks up some of the iron while in the molten pool. Therefore, hot chamber machines are primarily used with zinc, tin, and lead-based alloys. Cold chamber die casting. These are used when the casting alloy cannot be used in hot chamber machines. These include aluminium, zinc alloys with a large composition of aluminium, magnesium and copper. The process for these machines starts with melting the metal in a separate furnace. Then a precise amount of molten metal is transported to the cold chamber machine where it is fed into an unheated shot chamber. This shot is then driven into the die by a hydraulic or mechanical piston. This biggest disadvantage of this system is the slower cycle time due to the need to transfer the molten metal from the furnace to the cold chamber machine. Mold or tooling. Two dies are used in die casting. One is called the cover die half, and the other the ejector die half. Where they meet is called the parting line. The cover die contains the sprue or shot hole, which allows the molten metal to flow into the dies. This feature matches up with the injector nozzle on the hot chamber machines or the shot chamber in the cold chamber machines. The ejector die contains the ejector pins and usually the runner, which is the path from the sprue or shot hole to the mold cavity. The cover die is secured to the stationary, or front, plate of the casting machine, while the ejector die is attached to the movable plate. The mold cavity is cut into two cavity inserts, which are separate pieces that can be replaced relatively easily and bolt into the die halves. The dies are designed so that the finished casting will slide off the cover half of the die and stay in the ejector half as the dies are opened. This assures that the casting will be ejected every cycle because the ejector half contains the ejector pins to push the casting out of the die half. The ejector pins are driven by an ejector pin plate, which accurately drives all of the pins at the same time and with the same force, so that the casting is not damaged. The ejector pin plate also retracts the pins after ejecting the casting to prepare for the next shot. There must be enough ejector pins to keep the overall force on each pin low, because the casting is still hot and can be damaged by excessive force. The pins still leave a mark, so they must be located in places where these marks will not hamper the casting's purpose. Other die components include cores and slides. Cores are components that usually produce holes or opening, but they can be used to create other details as well. There are three types of cores: fixed, movable, and loose. Fixed cores are ones that are oriented parallel to the pull direction of the dies, therefore they are fixed, or permanently attached to the die. Movable cores are ones that are oriented in any other way than parallel to the pull direction. These cores must be removed from the die cavity after the shot solidifies, but before the dies open, using a separate mechanism. Slides are similar to movable cores, except they are used to form undercut surfaces. The use of movable cores and slides greatly increases the cost of the dies. Loose cores, also called pickouts, are used to cast intricate features, such as threaded holes. These loose cores are inserted into the die by hand before each cycle and then ejected with the part at the end of the cycle. The core then must be removed by hand. Loose cores are the most expensive type of core, because of the extra labor and increased cycle time. Other features in the dies include water cooling passages and vents along the parting lines. These vents are usually wide and thin so that when the molten metal starts filling them, the metal quickly solidifies and minimizes scrap. No risers are used because the high pressure ensures a continuous feed of metal from the gate. The most important material properties for the dies are thermal shock resistance and softening at elevated temperature. Other important properties include hardenability, machinability, heat-checking resistance, weldability, availability, and cost. The longevity of a die is directly dependent on the temperature of the molten metal and the cycle time. The dies used in die casting are usually made out of hardened tool steels, because cast iron cannot withstand the high pressures involved, therefore the dies are very expensive, resulting in high startup costs. Metals that are cast at higher temperatures require dies made from higher alloy steels. The main failure mode for die casting dies is wear or erosion. Other failure modes are heat checking and thermal fatigue. Heat checking is when surface cracks occur on the die due to a large temperature change on every cycle. Thermal fatigue is when surface cracks occur on the die due to a large number of cycles. Process: the following are the 4 steps in traditional die casting, also known as high-pressure die casting. These are also the basis for any of the die casting variations: die preparation, filling, ejection, and shakeout. The dies are prepared by spraying the mold cavity with lubricant. The lubricant both helps control the temperature of the die and it also assists in the removal of the casting. The dies are then closed and molten metal is injected into the dies under high pressure, between 10 and 175 megapascals. Once the mold cavity is filled, the pressure is maintained until the casting solidifies. The dies are then opened and the shot is ejected by the ejector pins. Finally, the shakeout involves separating the scrap, which includes the gate, runners, sprues and flash, from the shot. This is often done using a special trim die in a power press or hydraulic press. Other methods of shaking out include sawing and grinding. A less labor-intensive method is to tumble shots if gates are thin and easily broken. Separation of gates from finished parts must follow. This scrap is recycled by remelting it. The yield is approximately 67%. The high-pressure injection leads to a quick fill of the die, which is required so the entire cavity fills before any part of the casting solidifies. In this way, discontinuities are avoided, even if the shape requires difficult-to-fill thin sections. This creates the problem of air entrapment, because when the mold is filled quickly there is little time for the air to escape. This problem is minimized by including vents along the parting lines. However, even in a highly refined process there will still be some porosity in the center of the casting. Most die casters perform other secondary operations to produce features not readily castable, such as tapping a hole, polishing, plating, buffing, or painting. Inspection. After the shakeout of the casting it is inspected for defects. The most common defects are misruns and cold shuts. These defects can be caused by cold dies, low metal temperature, dirty metal, lack of venting, or too much lubricant. Other possible defects are gas porosity, shrinkage porosity, hot tears, and flow marks. Flow marks are marks left on the surface of the casting due to poor gating, sharp corners, or excessive lubricant. Lubricants, water-based lubricants, called emulsions, are the most commonly used type of lubricant, because of health, environmental, and safety reasons. Unlike solvent-based lubricants, if water is properly treated to remove all minerals from it, it will not leave any byproduct in the dies. If the water is not properly treated, then the minerals can cause surface defects and discontinuities. There are 4 types of water-based lubricants: oil in water, water in oil, semi-synthetic, and synthetic. Oil in water is the best, because when the lubricant is applied the water cools the die surface by evaporating while depositing the oil, which helps release the shot. A common mixture for this type of lubricants is 30 parts water to 1 part oil, however in extreme cases a ratio of 100 to 1 is used. Oils that are used include heavy residual oil, animal fats, vegetable fats, and synthetic fats. HROs are gelatinous at room temperature, but at the high temperatures found in die casting, they form a thin film. Other substances are added to control the emulsion's viscosity and thermal properties. These include graphite, aluminium, and mica. Other chemical additives are used to inhibit rusting and oxidation. Emulsifiers are added to water-based lubricants, so that oil-based additives can be mixed in the water. These include soap, alcohol esters, and ethylene oxides. Historically, solvent-based lubricants, such as diesel fuel and kerosene, were commonly used. These were good at releasing the part from the dies, but a small explosion occurred during each shot, which led to a buildup of carbon on the mold cavity walls. However, they were easier to apply evenly than water-based lubricants. Advantages and disadvantages. Advantages of die casting: excellent dimensional accuracy and 0.02 ohm for each additional centimeter. Smooth cast surfaces. Thinner walls can be cast as compared to sand and permanent mold casting. Inserts can be cast in. Reduces or eliminates secondary machining operations. Rapid production rates. Casting tensile strength as high as 415 megapascals. Casting of low fluidity metals. The main disadvantage to die casting is the very high capital cost. Both the casting equipment required and the dies and related components are very costly, as compared to most other casting processes. Therefore, to make die casting an economic process, a large production volume is needed. Other disadvantages are that the process is limited to high fluidity metals, and casting weights must be between 30 grams and 10 kg. In the standard die casting process, the final casting will have a small amount of porosity. This prevents any heat treating or welding, because the heat causes the gas in the pores to expand, which causes micro cracks inside the part and exfoliation of the surface. Variants. Acrorad. Acrorad was a die casting process developed by General Motors in the late 1950s and 1960s. The name is an acronym for accurate, reliable, and dense. It was developed to combine a stable fill and directional solidification with the fast cycle times of the traditional die casting process. The process pioneered 4 breakthrough technologies for die casting: thermal analysis, flow and fill modeling, heat-treatable and high-integrity die castings, and indirect squeeze casting. The thermal analysis was the first done for any casting process. This was done by creating an electrical analog of the thermal system. A cross-section of the dies were drawn on teledeltos paper and then thermal loads and cooling patterns were drawn onto the paper. Water lines were represented by magnets of various sizes. The thermal conductivity was represented by the reciprocal of the resistivity of the paper. The Acrorad system employed a bottom fill system that required a stable flow front. Logical thought processes and trial and error were used because computerized analysis did not exist yet. However, this modeling was the precursor to computerized flow and fill modeling. The Acrorad system was the first die casting process that could successfully cast low-iron aluminum alloys, such as A356 and A357. In a traditional die casting process, these alloys would solder to the die. Similarly, Acrorad castings could be heat-treated and meet the U.S. military specification MILA 21180. Finally, the Acrorad system employed a patented double-shot piston design. The idea was to use a second piston to apply pressure after the shot had partially solidified around the perimeter of the casting cavity and shot sleeve. While the system was not very effective, it did lead the manufacturer of the Acrorad machines, Ube Industries, to discover that it was just as effective to apply sufficient pressure at the right time later in the cycle with the primary piston. This is indirect squeeze casting. Pore-free. When no porosity is allowed in a cast part, then the pore-free casting process is used. It is identical to the standard process except oxygen is injected into the die before each shot to purge any air from the mold cavity. This causes small dispersed oxides to form when the molten metal fills the die, which virtually eliminates gas porosity. An added advantage to this is greater strength. Unlike standard die castings, these castings can be heat-treated and welded. This process can be performed on aluminium, zinc, and lead alloys. Heated manifold direct injection. Heated manifold direct injection die casting, also known as direct injection die casting or runnerless die casting, is a zinc die casting process where molten zinc is forced through a heated manifold and then through heated mini nozzles, which lead into the molding cavity. This process has the advantages of lower cost per part, through the reduction of scrap and energy conservation, and better surface quality through slower cooling cycles. Semi-solid. Semi-solid die casting uses metal that is heated between its liquids and either solidus or eutectic temperature, so that it is in its mushy region. This allows for more complex parts and thinner walls. See also, fusible core injection molding, die cast toy, notes. References. Bibliography, Davis, J., Tool Materials, Materials Park, ASM International, ISBN A978-087170-545-7 DeGarmo, E. Paul. Black, J.T. Cusa, Ronald A., Materials and Processes in Manufacturing, Wiley, ISBN A0-471-65653-4, Andreessen, Bill, Die Casting Engineering, New York, Marcel Decker, ISBN A978-0-8247-5935-3. External links, die casting information and FAQs, tolerances for die casting, general die casting design datasheet.